This is a demo of the OpenArc avatar tracking project. Our contribution will be a module to the OpenArc library that will allow users to reconstruct and track a low-dimensional deformable avatar. Our system takes in a sequence of RGB images as input from the Azure Connect camera, and then fits the avatar model to the observed data.
A sophisticated avatar tracking system will allow users to appear as themselves or as a customized character in virtual environments. Here, we work towards this goal. Our system runs in real time on a single i5 laptop CPU and fits the body shape and pose simultaneously as the user moves.
Our current system uses the popular simple human body model. While missing finer detail, the model contains parameters to control the rotation of each joint, as well as the approximate body shape, and is cheap to store and send over the network.
At a high level, our system processes one frame from the depth sensor at a time. For each frame, after performing basic background subtraction, we segment the input image into a set of body part point clouds using a random forest. The body model is then initialized with the pose and shape from the previous frame and optimized part by part. Our evaluations show that the system works well in cases of severe self-occlusion and rapid movement, and recovers almost immediately from tracking failure. It produces reasonable results even if parts of the body are occluded by objects, since we include a model on likely human poses as part of the optimization algorithm. Finally, as part of a Ford University research project, we also investigated use cases of avatar tracking in the car. Primarily, we looked at how to best set up a camera in the car and worked on integrating a face landmark detection algorithm from OpenCV.
So what you are seeing here is an example of our facial landmark detecting algorithm before we test it on our in-car dataset. So there are three main things. The first is the blue bounding box around the face, which is detected every frame. Next, in red, we have 8 facial landmarks around the eye, nose, and mouth, which are detected every frame. And in green, we actually have tracked landmarks from the previous frame that become reinitialized if the tracking fails or if they are too far from newly detected landmarks. This is to help us in cases where we cannot detect new facial landmarks, which you should see in the in-car dataset to follow. So what you are seeing here is an example of our in-car dataset. What you should notice is that in the frames where we failed to detect new facial landmarks, which are red, our green tracked landmarks from the previous frame do kind of remember where the previous landmarks were, and we show that on the face. So what you're going to see here is an ideal use case, which is when the driver is looking towards the camera. You should notice that both the newly detected landmarks and tracked landmarks are fairly accurate in terms of where they should be on the face. So in this next section, you're going to see some cases where our algorithm fails. This is mostly when the driver is looking away from the camera. As you can see, both detected and tracked landmarks are in the wrong positions on the face. We propose this is kind of a place for future work for any continuation of this project. This has been a small demonstration of what we worked on this semester as part of the OpenArc avatar tracking project. Thank you for listening.